we're going to go ahead and start talking about kind of putting everything together with our sampling distributions. Yesterday you took data. Yesterday you did the proportion of blue M&Ms that you had. Okay, and so then this P hat was your proportion of blue M&Ms, and so each one of you did that. And what were your sample sizes for these? 50. What? Good. You had a 50 randomly selected M&Ms. Good. And then over here on the right, you did times. So you made an X bar out of how many times? 30 times. And it was the average of your times when you tried to get what? When you tried to get 5 seconds on your timer. Okay. Very good. So let's talk about, so the first thing I want to do is really understand the difference between population distribution and this thing called sampling distribution. Okay, that's first and foremost. That has to be absolutely nailed down and solid. So let's first talk about the population of our M&Ms. So do you remember this situation where we had our, let's see if I have it here. Aha. Remember this here? So where we are told that 20% of our M&Ms are blue coming out of the factory. And I had kind of played the trick on you guys and asked you, what's the shape of this distribution? What ended up being the situation on this? You cannot say the shape of this because it is categorical data. So that means for this one, we do not have a shape. So there is no shape to the population. Okay, but the way to be able to make a distribution that has a shape was making this thing here. This is a shape made up of samples. Hence, this is called anybody? Sounds like Bueller. It's a sampling distribution because it is a shape made up of samples. Okay, sampling distribution because it's a shape made up of samples, which was extremely important since our population of blue M&Ms is categorical and has no shape. All right, now let's talk about the means. You each took 30 times, and there were 128 students. That means yesterday there were 3,840 times calculated throughout the course of the day, and that's the that's the population. Those 3,840 times that my students tried. Do we know the shape of those 3,840 individual times? Did we graph all of the times individually? No, we did not. We did not graph the shape of the items individually. So take a look here. See this black distribution up on top? I am just throwing it out there because I don't know, but let's just pretend like this shape up here on the top is the 3,840 individual times that you guys did yesterday. So that's a whole lot of individual times. Obviously, that's why we wouldn't graph it, is because that's a ridiculous amount to have to plot. So if we don't know the shape of the population, or if it's something that is just ridiculous to come up with, or it's messed up, then so this would be considered our population. And because let's talk about what happened here on this picture to the right. We do not know the shape of the what? We do not know the shape of the population because we didn't plot 3,840 times. So we do not know the shape of the population. Hence, is it reasonable to predict the proportion of your times that were more than 5.1 seconds? Can I use that up there and calculate the proportion of times more than 5.1 seconds? No, it's not a shape that I can calculate with. It's not unimodal, symmetric, and approximately normal. So no, I cannot. All right. So since we do not know the shape of the population, or we can't compute with it, then look at what we did. What is this called that we made here? What is this green thing called? Well, it's unimodal symmetric, but it is called a sampling distribution, because it is a distribution of sample what? This is a distribution of sample what's? Means. X bar is a sample mean, and to the left, this one on the left was a distribution of the sample proportions. This is a distribution of sample proportions, or otherwise known as p hats. Thank you. And on the right, this is a sampling distribution of sample means, otherwise known as X bars. Okay, so that's what the big deal about sampling distribution is. Either we don't have a population to shape, or we don't have a clue what the shape is, or we do know the clue, we do know what it is, and it's something that's messed up and I can't compute with it. Therefore, we have our sampling distributions. Okay, so that is the first main thing, understanding what the population distribution is and comparing it, and talking about the importance of this sampling distribution, these two things right here. Okay, next we want to talk about the notation for lots of little things here. So we're going to take what does notation mean? The shorthand of something. We're going to look at the symbols of how you write and notate all these different things that we're doing, whether it's symbols for the population or symbols for a sampling distribution. Okay. And the first thing we're going to do is just kind of discuss them. Here, I'm kind of all over the place in your packet this year because I've switched up the lessons. I'm going to fix this better for next year to be in a more cohesive way. But so you're going to be all over the place today. Start on page 49 here. And we'll go through these. Kind of already talked about it, so here we go. Review these sampling distributions. First thing I said was proportions have no parent population because they're categorical. But we can make a distribution of p hats. Now, why are all those p hats different? What makes your p hat different from my p hat? Random sampling. Sampling variability. Sampling variability happens because you got different data than me. Okay, and so when we take a look at our results, we want to be able to describe its distribution. And how do we describe the distribution? We do its shape and outlier, center and spread. Okay, so let's take a look at those on our proportion problem. So here we go. Let's take a look at that here. What would you say is the shape of this one on the left? Unimodal and somewhat symmetric. Okay, it's not perfect, but somewhat symmetric. Okay, so shape, unimodal, somewhat symmetric. Okay, outliers. So I actually can calculate the outliers. I took the center, these looked to be centered around the 20%. And from that, so let's actually go to center. What was the claim? We're going to say that this factory claimed that there would be the average of 20% blue M&Ms. Okay? How do I get the spread? How would I compute the standard deviation of all of those p hats? Do you remember how to do that?
P times P minus 1, 1 minus P over N.
Perfect. Over n, and then you square root it. Well, I did that, and it comes out to 5.6%. To make it simple, it was about a spread of 6 percentage points. Hence, one standard deviation up is at 26%, and the next standard deviation up is at 32%. So let's look at the outliers. What did we have yesterday? How many outliers did we have? We had 4 upper outliers. Okay, let's go down 1 and 2 standard deviations. Did we have any lower outliers? No, we did not. Okay, so we just described our distribution, and we were specific. We specifically stated the center's values. We said there were 4 upper outliers, and we would identify those. They weren't too bad outliers. It was reasonable. There was nobody more than 3 standard deviations out, so nobody was freaking me out with their data. And our standard deviation was 6%. Okay, so we described that distribution. Now let's just really nail down these variables right here. Plain old P is the population proportion. I think that makes sense. The mean of the P hats is certainly going to be where the center of all of those what? The sample proportions are, okay? And then the sigma of the P hats is certainly going to be what? How spread out all your P hats are. Okay, so I hope that these notations follow along with what we're talking about and make sense. All right, let's move on. Means. We talked about that already. But we didn't actually just, the mean, mu, would be the population's mean. And if we were talking our seconds, what would we expect the population average to be? Of all times trying to get on, that we were trying to get on the timer. What would 5 seconds. Yep, the population mean is going to be what we expect it to be. So even though this example on this paper has some other numbers or has another situation, we're going to go with this. So I went through and I found the population standard deviation because I had like tons and tons and tons and tons of data. And so I came up from past years. So the population standard deviation, I can't remember what it was, but we'll come back and visit this. All right. So let's just do a quick little thing and recall some of these letters. Okay, you ready? Whatever the population is, if I don't know the shape of the population, let's say I don't know it, but it is filled with individual pieces of data. We had how many pieces of data that we collected yesterday? 3,840. There were 3,840 times that we would have to plot and see what the population looks like, which may be that one right up there. Okay, so each X is representing one randomly selected time that you did on your stopwatch. Then, if you took little X bars, say you had done little samples of size 2, then they would drop down, and then, of course, samples of size 25. So what happened as we got larger sample sizes? Got more compact data, the standard deviation got smaller. So I actually want to show you that here with our funky population this may be representing our 3,800 times, okay? So watch this. I'm going to do an animation of two randomly selected items and then get their X bar. And then this doesn't go up to 30, so I'm going to do 25 times. So here we go. Watch this. 2 times. And that is that blue right there is the X bar of 2 times. Now this is taking out 25 randomly selected times and going to average those. There's the X bar of 25 times. Already, I'm liking this where that average landed, that X bar of 25 better. Okay, let's do it again. 2 times, and that average is there. Now here comes 25 times. 25 individual X's dropping down and going to make an X bar. Here it goes. Oh, dang. Look at that. So close. Let's do that just one more time. 2 X's. There's its X bar of 2 X's. Now, last one. 25 of them. 25 individual X's. Gonna X bar down here. There it is. Okay. Now, let's do it a bunch of times. Here we go. Speeding the process up. Look at what's happening here. Do you feel as though it is reasonable for you to do normal model math and compute normal model probabilities on this second shape here where there is an N of 2. Sample size 2. I don't think so. So, but what about this one with the sample size of 25? That one's looking pretty darn good. Okay. In fact, if it was 30, like our sample sizes were, it'd be even better than that. Okay. The larger your N, the better this is getting. And we're going to see that here in just a second. So when we take a look at this page, let's notice, okay, let's go ahead and describe our distribution for your times yesterday. All right, let's do it. Let's describe the distribution of your times right here on the right. Here's the green ones. What do you want to say the shape is? Unimodal, somewhat symmetric. We'll come back to outliers. So the shape, unimodal, somewhat symmetric. Center, where did this seem to be centered at? Okay, the mean of 5 seconds. I've in the past calculated the standard deviation of this to be 0.08. The spread was 0.08 of this sampling distribution to be 0.08 seconds. And so, look, 1 standard deviation up, 2 standard deviations up, 1 standard deviation down, 2 standard deviations down. Did we have any outliers? Just these little 4 here. So we did good. We just had 4 outliers in each one of our distributions. Okay, so we would say 4 upper outliers. All right, so that's our describing the distribution, shape, center, spread, and the outliers. So coming back to now on your page 51 is the notation here. X bar, of course, is your sample mean. Okay, so look at this mu. This mu is going to be the average of what? All of the X bars. So that's the sampling distribution. All those X bars are going to average out to be that amount. And then all of the X bars will have that standard deviation. So that's how spread out the X bars are. All right. So now that we've kind of gone through that notation, I want to take a moment and let you skip on over to page 34. I'm sorry, you're going to have to skip back to page 34 because I'm going to let you take a few moments and see if you can't match your notation with the definitions. Okay, so take a few moments to do that. Go. All right, let's check here what you did. Okay, actually, I like to do this one right here. I like to go this way. Mean of the population. What number does A go to? Mean of the population. Yep, right here. That regular old mu. Okay, standard deviation for the whole population. Where's that one? Okay, good. Number 7. All right. What represents your sample size? N is number 4. That's C. Sorry, C. Okay, how about an individual piece of data? All your 30 little times. That's the regular old X. That's number 3, the regular X. Okay, sample mean, your average of your 30s. That's your X bar. Very good. All right, average of all of those X bars. Average of all those mu X bar. Very good. So that's, I think F goes right there. Okay, how about standard deviation of all those X bars? Sigma right there of the X bars. Okay. Next, population proportion. That's plain old P. That's number 9. Sample proportion is your P hat, number 11. And average of all of the P hats. Okay, that's number 2. And then the last one, standard deviation of all the P hats, is number 1. Okay. So listen to me, people. The idea is you have got to know in your brain that these individual pieces of data have to do with the population. So these individual pieces of data go in the population. Okay? And how about this next one? All of these p-hats go have the mean of the p-hats and the standard deviation of the p-hats. And finally, how about the x-bars? All of your sample x-bars go with the mean of x-bars and standard deviation of x-bars. Okay, so that's what's happening for you to be able to read a problem and also write out your notation correctly. Very good. Okay, so scoot on over to page 43. We're now going to actually learn something we've been talking about already, but do it by name of the actual theorem. Page 43. Okay, here we go. So, central limit theorem. You have to know this theorem by name, and it has to do with the shape of the population and the shape of the sampling distribution. Okay? And we're talking about what is needed for it to be approximately normal or have that unimodal symmetric shape. Okay. So, of course, I have a song that represents this. Remember that the other idea that you had to know by name was with the penny thing that we did, where all of those settle down to this theoretical probability, is that law of large numbers. Okay. So, law of large numbers, we have to know by name. Central limit theorem, we have to know this. So, let me kind of mention what's happening with this. This here can kind of, let's see. This here is a good way to demonstrate what the central limit theorem is saying. Central limit theorem says that we may or may not know the shape of this population. Okay, that's the part up here that's black. So we may or may not know the shape of the population, but we know that if you meet the criteria, and in particular, if the sample size is large enough, then your shape, your sampling distribution will be approximately normal. So look at the top black area is the population. Look at this first blue section, and here in the middle, what was that a sampling distribution made up of? What size samples were those? Size 2. And it did not fix the problem in the population. But look at the bottom one. It's supposed to be 30, but this applet does samples of size 25. It's supposed to be 30. Then did it fix the problem from our population? Yes, it did. So in summary, if n is large enough, then it doesn't matter the shape of the population. The sampling distribution's about normal. Okay, so and we'll play that here in just a second. So that's what our central limit theorem is going to be saying. And actually, because of the recording, I'll have to do it separate, like at the end. Okay, so you're kind of going to not get the full effect of the song right this very second. But it says that if n is large enough, then it doesn't matter the shape of the population. The sampling distribution's about normal. Okay, so do you see this picture? I love this picture. Here are 3 shapes that are no good. I cannot do normal model math on these populations. And look at n equals 2. Did sample size n equal 2 fix the problem? No. These ones did not fix the problem, but did a sample size of 30 fix the problem and make it about normal? Yes, it did. And that's what our central limit theorem is. It's about the shape of the population and the sampling distribution. Now, let me give you just one little other caveat here. The central limit theorem, since it is about the shape of both the population and the sampling distribution, then that actually means that technically, in all the reality is it's meant for means only. It's meant for your x bars only, because the x bars have a population shape. Remember this? what we discussed at the beginning of the lesson. Your X bars, right over here on the right, your X bars have a population shape. We just may not know it. What did we say over here on the left? Those P hats do not have a population shape because they were categorical. So in all technicalities, central limit theorem applies to the means. However, the proportion problems follow along the same kind of thinking. We just have a different rule for what makes them large enough. Okay, so let's find out what are those magic rules that we will be writing over and 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 over again this year, from now until infinity and beyond, about what makes the magic of the sampling distribution be normal. Here we go. We're going to do this. We're going to write it out first with our sample that we did with our M&Ms, okay? So I'm going to use the color blue to represent our M&Ms in blue that we did yesterday. So what we got to do is get real. R-I-L. Okay, no, that's not like a national thing. People, that's not normal. So I mean, that's just Miss McClellan helping you remember to see if it's gonna be good to go. We got to get real, and let's get down to it. So the thing is, you can't just write R-I-L. You have to write out the words. So no shortcuts. Okay. So the first thing we would do in our conditions is we would say, or our assumptions, we would say random. That's the first thing that has to happen. And colon. And then we have to read the problem and see if the data was randomly selected. So do you think it's reasonable to assume that your M&Ms were randomly selected? Okay, good. So I think that we can assume that we have randomly selected M&Ms. So that's exactly what you were right. And I will only write the minimum. I mean, I'm going to write the minimum here. I'm not going to add a whole bunch of stuff because I know it's a pain, but I will write the minimum. So everything here is what has to be there. Okay. I stands for independent. What have we learned this year that is so important that independence tells us? What is independent? Independent. The fact that you are one thing does not change the rate. So the probabilities are what? Not changing from sample to sample. Okay, so here, I want you to, this is very important. Visualize right now the factory that these M&Ms came from and the assembly line with all of these billions and billions of M&Ms rolling down the assembly line, okay? Rolling down the assembly line. 20% of them are blue. You walk up to it and you scoop a little cup of your 50 M&Ms. Got it? And now you're going to then figure out what you got there. Okay? And you think you're going to have about 20% blue. Then somebody comes a minute behind you and they take their cup and they scoop 50 M&Ms. Is their probability different because you have taken your scoop of 50 M&Ms? Why not? Because there's just so many. The population is so big, your little sample is not really affecting the probability. That's what this independent is saying. It's saying my 50 M&Ms is so insignificant compared to the population. And my 50 M&Ms is certainly less than or equal to 10% of all M&Ms. Okay, so that's how you would write that. Okay, and finally, L stands for large enough. Large enough is tricky because it all depends if this is a mean or a proportion problem. There's actually two different rules. There's a rule for the means and a rule for the proportions. So since we're doing proportions, we'll go down to this rule. Here it is. Here is our large enough for our M&Ms. Here's how we would write large enough is tricky because it all depends, mean or proportion. Means are 30 to be large enough, but proportions have to have at least 10 successes and at least 10 failures. That means I have to show this computation, okay? So what was our N for our little cup of M&Ms? We picked 50. Okay, good. So that's the N, 50. What was the P, the population proportion of blue? What was our population proportion of blue out of the factory? 20%. So I go N times P. And how much is 50 times 0.20? Haha, 10. Is that greater than or equal to at least 10 successes? Yes, it is. That is the reason your sample size was 50. Because Miss McClellan, in her infinite wisdom, knew that we needed to have that 50 to meet this criteria. Okay, but we can't finish, or we're not finished yet. We have to do 50 times the proportion of failures. There's 20% that are blue, 80% are not blue, which is 40, which is certainly greater than or equal to 10. So we have had randomly selected M&Ms. Our sample was less than 10% and not changed the probability, and we showed large enough. So we finish saying the approximately, I don't know if it's perfectly normal. Was our little sampling distribution perfectly normal? Approximately normal. Model applies. That's how we finish everything up. That was the goal. So now I have the right to do z-scores and normal model math and tell you whatever you want to know. Okay, let's repeat this with the M&Ms. I'm sorry, my bad, with the times. Okay, so I'm going to do this in a different color. Let's repeat this with the other data you did yesterday. Let's see if we were good to go for our other data. Random. Do you think it's reasonable that we had randomly selected, yours are randomly selected times, or that they're representative of regular times? I mean, okay. I think they're randomly, so I'm going to have to assume that they are randomly selected times. In essence, you're kind of saying, I really think that mine are just as representative as the next ones. Okay. All right. Then I write the word independent. Do you think what you get on one changes the probability of the next? No, I do not. So you can write that out. You could say one time doesn't affect the probability or what you get on the next one. Okay, but you also can always say, here in this case, I know that my 30 times is going to be less than 10% of all. So my 30 times is less than 10% of all times taken on the timer. And large enough is tricky because it all depends. Mean or proportion. Means has a different large enough rule than proportion. So the large enough for means is this right here. My 30 times has to be greater than or equal to 30. Was it? Ding, 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 ding. Yes, it was. So do you think there was a magical reason why Miss McClellan had you do 30 times? That was it. Okay, so we aren't finished with this. We have to say approximately normal model applies. So that's like your conclusion. You're wrapping it up and saying, yeah, it's approximately normal sampling distribution. I am good to go, and I'm good to compute all the normal model math you want me to. Okay, so that is the important criteria that the central limit theorem says. If you meet these, then normal model math is a go, and we are good to go. And so in summary, we wanted to make sure that we had that understanding of the population, sampling distribution, that notation, getting those assumptions. And then we'll talk a little bit more about this as n gets larger at another time, on Tuesday. So you have to do your assignment, which is pages 46 to 48. Now, I know that it very well could be Monday night or Tuesday flex when you're doing this. I hope not Tuesday flex, because I think this assignment will take longer than 25 minutes, okay? It's probably going to be a 40-minute assignment. So I am going to be making about a 10-minute video of me doing page 46 because so that you make sure you get all the details in there just right. I just didn't have enough time with this. So please watch the 10-minute video of me doing page 46 to get you going on this assignment, 46 to 48.